Cool. We're live. Hey, everyone.
Great. Hey, everyone. How's it going? I want to welcome you all to the much delayed, much belated final installation of the Escarpment Labs webinar series, Season 1. The conclusion to Season 1 took a long time to come. Just think of it as the yeast equivalent of Who Shot Mr. Burns. We're not gonna keep you waiting all summer this time, though. So you're gonna find out who soured the wort, I guess. I want to thank you for sticking in with these. This has been a lot of fun. Nate and I and the rest of the team have had a lot of fun putting this stuff together, chatting with all of you, putting stuff up on YouTube. We're going to keep doing that. We are going to be taking a little bit of a break just to sort of put together some new content, just try to keep the quality level high. We still have no shortage of things to talk about. We have a little bit of a loose schedule built out until December, believe it or not. So definitely keep your eyes peeled for some content for us. But, I think I can speak for the both of us that we need a little bit of a break to just sort of reflect and, figure out where we want to take this thing, and also just focus on getting as much yeast to as many brewers as possible, because it's the summer and people are thirsty.
Yeah, we're also in the middle of an expansion, and there's a whole bunch of other stuff going on. So we honestly just need time to get figures and things like that together, and get images and make sure everything's nice and polished up. So,
yeah. So we're going to be back probably mid-July. We're going to be Nate's going to be presenting on yeast management. I know that's something that people are asking us about a lot. If you want to know, best practices for yeast repitching, checking the health of your yeast, really easy ways to manage your yeast and get more value out of it. That's what we're here for. At the end of the day, if your yeast is crapping out on Gen 4 and you weren't planning on reordering till Gen 7, then that's a problem for us too, because then we have to scramble to make sure that we have that yeast available.
That series on yeast management is going to be a series, a multi-part series on it, not just one lecture. So we're going to be covering a lot of content. If yeast basics was a kind of 101, this is going to be 201.
Absolutely. Yep. And we're going to be posting some shorter videos on our YouTube as well. So just look forward for that. Just trying some different experiments, see what everyone's interested in, and take it from there. We love talking about yeast, so we're going to keep trying to find ways to do that. Okay, so without further ado, our topic for today is quick souring with Lactobacillus 101. I think this is also a really important area. Something we get asked about all the time is, what's the best way to make a quick sour or a kettle sour? What lactose should I use? What temperature should I use? Do I need to boil it? How long should I boil it? These questions are, endless, and we've done our best to try to answer as many of them as possible. That being said, if you have any questions during the webinar, feel free to ask a question down below. Feel free to, chime in the chat if something's not clear as well. I'll do my best to try to follow up and answer, and really enjoy. I'm really looking forward to this talk. So if you want to take it away, Nate.
Also, one thing before I forget, if you have questions when you're watching videos on YouTube, put them in the comments below too. I've been scanning those about once a week or so to make sure any questions that come up, we can kind of, pick those questions, make sure we answer them in later webinars, things like that. We are watching those things, just as a heads up. But yeah, with that, we'll kind of get straight into it now. Oh, here we go. There we go. Aha, wonderful. So today we are going to be talking about kettle souring, as Richard mentioned. And one thing I just want to let everyone be aware of, about 4 to 5 years ago, I gave a talk on kettle souring on the Canadian Brewing Awards. And it was a relatively new technique. It was relatively modern. No one really knew a huge amount about it. And since then, little bits of information on this technique have just been kind of feeding themselves out over the last handful of years. I underestimated how much content has come out on this topic since. It's been a slow, kind of steady feed of information, and I was a little overwhelmed, honestly, when I actually had to put down to paper how much content us and other yeast labs have come out with on kettle sours. Now, with that being said, there are some things for kettle sours that's are a little contested, or some areas where one lab might recommend A while we recommend B. We're going to be covering today about what we recommend, and we're going to be defining the reasons why. There are a few things that we differ for some other suppliers, and that's okay. This is what we're talking about today, about the stuff that we have data for, and we're going to make some decisions and make some recommendations based on that data. And with that, we're going to get started. So, quick souring Lactobacillus 101. Before we get started as well, I just want to give a big thanks, a shout out to Iz Neto. She was one of our lead researchers, who unfortunately she no longer works for us. But she's one of the ones who did most of this research. It made a handful of figures that we're using today. I just wanted to give her a shout out. We'll see her again at the very end of the presentation as well. And as always, there's a little bit of a disclaimer. The goal of this presentation is to teach you to make you better brewers. So there are certain portions where I might glance over some of the small details or some areas where we don't have all the knowledge yet. Additionally, I'm assuming that you've watched the Yeast Basics series for today. So if I say something or refer to that, it's going to be in that content. And just as always, make sure if you have questions, put them down below. So quick souring has a lot, or kettle souring, as it's kind of often called. There's a lot of complexity to it. And we're going to kind of break it down today into 5 main stages. We're talking about what kettle souring or quick souring is, what lactobacillus is and how it works. That's the main organism that play. How we control a quick sour, so what things we can use to actually manipulate the flavor profile one way or the other. Common problems and techniques with it, and then finally some new research and kind of some advanced techniques or some kind of things you might be thinking of trying, and the issues or problems or benefits of them. So we're going to start from the top. What is a quick or kettle sour? Well, a quick sour, in its simplest form, is a method of producing sour beer in a conventional brew.
For a second, we can't see your slides.
Oh, that's important, isn't it?
Okay, we got it now.
Awesome. Still?
You're all good.
Wonderful. So yeah, we're going to break it into the 5 different sections, as said before. So a quick sour is just a method of producing sour beer in a conventional brewery, and this is the important bit, without the cross-contamination risk present that historical methods would have. Now, a historical method would be adding lactobacillus into the beer itself, letting it sour naturally, or via the addition of this culture. The big change here is that with these old methods, you have live lactobacillus in your filter, in your packaging lines, in your canning lines, everywhere. You have this organism present throughout your entire facility, which means that it poses a risk to other brands. You might sporadically have other brands becoming sour or becoming contaminated unintentionally. Kettle souring means that you can handle all your beers clean and everything. The risk of having cross-contamination essentially is 0. Now, this technique, as you'd expect, implements lactobacillus to sour the wort, usually in a dedicated vessel, which is often the kettle. However, that's becoming less and less common. Followed by a secondary boil to eliminate the risk of the live lactobacillus. This allows the brewer to treat this sour beer, to produce it quickly, but mainly to handle this beer like they would, say, a lager or an IPA or anything else relatively low risk. And that's the benefit. So a quick overview of the process you can see right here. So we have the wort we produce in the brew house the same way we normally produce a wort. 0 IBUs for this because lactobacillus is inhibited by IBUs. And you're going to cool the wort out into your kettle. Most breweries will then boil this at this point to sterilize the wort. They'll then add lactobacillus. So they'll cool the wort down. That's an important bit. Otherwise, you're just going to kill it. Cool the wort down. Add lactobacillus. This souring will then either occur in a fermentation vessel or the kettle, at which point it will then be boiled again and then transferred into the FV. We're going to talk about some of the different variations on this method you can go through, but that's kind of the basic premises. Now we can break this down into about 6 main steps. Convert your mash as normal in lauter, boil the wort to sanitize, cool the wort down to about 35 to 40 degrees Celsius to accelerate lactobacillus growth, inoculate the wort with lacto, reboil it to kill off the lacto, and then handle your beer as you would anything else. Now we're going to talk about steps 2 through 5 here because steps 1 and 6 are kind of standard. We don't need to talk about those. It's not important for today. But steps 2 through 5, those are where there's some details that we need to talk about because a lot of brewers don't fully understand these. So before we go into anything in regards to the kind of details, we have to go through the basics. What is lacto and how does it actually work? Without this, we really can't get deeper into this. So what is lacto and how does it work? Now, this is what Lactobacillus looks like. This is what we call a scanning electron microscope image. This is not what Lactobacillus is going to look like underneath your microscope. This image probably costs many thousands of dollars to create and probably took someone about several weeks to produce. It's this is not what your microscope is going to look like. Now, Lactobacillus does have a very human property to it. It's intrinsically human. Humans have essentially been associated with Lactobacillus wherever we have gone. Lactobacillus is one of these organisms that we see found in just tons and tons of food around us. It's in yogurt, it's in sauerkraut, kimchi, pickles, hot sauce. I watched a video a few days ago about making fermented Brussels sprouts with Lactobacillus. It's all fundamentally produced with Lactobacillus. Now, Lactobacillus it's very, very small. It's much smaller than say, Saccharomyces we saw in our previous lectures. And 40x magnification, it just looks like these small little bits under the microscope. They're usually rods, but quite long. And when you start going under more and more high intensity microscopes, you actually start to see these little rods. Now, if you're working with a cheap microscope, it might be difficult to see Lactobacillus. I know at the college we have a few not so great microscopes. It's near impossible to see the bacteria present. But if you have a good kind of middle of the line microscope, you shouldn't have any problems, especially if it's well maintained. And most importantly, it makes yogurt. Just a little Spaceballs reference in there. Now, Lactobacillus is impactful for a handful of reasons. And it's one of the main 4 things that we've seen used to preserve food: salt, fat, acid, and heat. But it's important because it's so easy to be found. It's found everywhere. It's found inside of plants. It's found on organisms all over the world. And the reason that it's useful is that it does produce, as the name suggests, lactic acid. And this lactic acid is what helps preserve the food, and that's why it's useful to us. Lactobacillus, or the lactic acid it produces, helps mean that other pathogenic organisms can't consume it. It preserves the food for us, so that, say, things like E. coli or Staphylococcus can't consume it, which means that when we consume the food, we know it is safe. Now, lacto does this by lowering the pH of the environment to about 3 to 3.5. The degree of pH it lowers it is very multivariable. But it prevents the growth of these toxic pathogenic organisms, which is why it's handy. And we can see that in this chart right here. So what we see here is different types of organisms: molds, yeast, Lactobacillus, Staphylococcus aureus, Acetobacter, Salmonella, E. coli, all these nasties. And the bands you see here are the pHs in which these organisms are active. And you can see right here that with pH, when we get to the lower end of the lactic acid content, none of these nasty organisms are able to survive. Once we really get below pH 4, all of these organisms are pretty much well done. They're not really able to ferment much lower. Now, there's always exceptions to this. There's always acid tolerant versions of each one of these organisms, but 90% of them, 95% of them are not going to be present. This is why Lactobacillus is so useful and so kind of profoundly tied to humanity. It's one of the things that's probably allowed us to survive, which is pretty neat. We owe it a lot. Now, much like Saccharomyces, when it comes to sugar consumption, Lactobacillus prefers simple sugars, prefers glucose as much as possible. And then it goes to the more complex sugars after that. Now, where Lactobacillus and Saccharomyces differ when it comes to metabolism is that, unlike Saccharomyces, where its main end byproduct is ethanol, Lactobacillus' main end byproduct is lactic acid. Now, a very simplified metabolism you can see right here is 1 glucose equals 2 molecules of lactic acid plus energy. This is overly simplified, very overly simplified. It gets much more complex. And the first level of complexity we have to look at is understanding the different subclasses of Lactobacillus. Now, there's 2 main subgroups we need to talk about, and those are homolactic and heterolactic. Now, homolactic are organisms that essentially are where the metabolism is more akin to the previous slide. 1 glucose goes in, 2 lactic acid comes out. This is an organism that's only able to produce lactic acid. Now, there's not a huge amount of them in the kind of line between this and the heterolactic, where Lactobacillus strains where the end byproduct is either lactic acid, ethanol, acetic acid, or other compounds. The line between these is kind of gray. It's more of a spectrum. It's not a clear division in the line. And as we learn more and more about these different types of Lactobacillus, this is becoming a bit more blurry based on what I've read. But based on the environment, the state, the health of cells, we can kind of influence these cultures to kind of be a bit more one than the other. Much like different lactobacillus are going to have different fermentative pathways. So each strain is going to bring its own unique metabolism. It's going to produce different flavor compounds, different amounts of acid, different amounts of other compounds present. And what we see here is just a really clear, easy breakdown of homolactic versus heterolactic. You see homolactic on the left-hand side where one glucose goes in and we get 2 molecules of lactic acid. Where on the right, we see 1 molecule of glucose in, and this is the unique part. We see 1 molecule of lactic acid and 1 molecule of ethanol. So it's kind of neat. Lactic acid, the heterofermentative lactic, actually has the ability to produce some small amounts of ethanol. The same thing we see yeast cells produce. Now, if you look at the metabolism we see here, the way in which it produces it is significantly different, but it does still eventually produce some ethanol. Now, we can further break this heterolactic pathway out even further. We can actually look at where the energy is being produced. So these heterolactic organisms produce ethanol and lactic acid, as we kind of see here. It's not well understood. And much like we saw with Saccharomyces, where glycolysis kind of drove most of the energy production, and then alcohol fermentation or anaerobic respiration didn't really consume anything, we see a very similar process here, where we go to xylose as the middle point. This is kind of the pyruvate analog for the lactobacillus metabolism, at which point that gets split into 2 different ways. Ethanol on the right-hand side, lactic acid on the left-hand side. The energy, one consumes energy, one produces energy, but most of the energy is produced in the top portion, in the glycolysis analog, so to speak. Don't push an analogy too far, because it kind of falls apart a little bit. And one thing I wanted to mention here, because it's going to come up probably at the end of the presentation, but it does also have the ability to produce acetate, which is heavily tied to a vinegar and acetic acid content. But we'll talk about that later. Now, when it comes to how much alcohol is actually being produced, we ran an experiment where we had 16 different lactose strains. We only saw that Lactobacillus kunckii and rhamnosus were able to produce measurable amounts of alcohol. And we're not talking huge amounts. We're talking 0.1 to 2% alcohol for these fermentations, not a large amount. I bring this up because some brewers get a little scared where they're worried about the ethanol being produced inside their kettle sour. And when they boil it, they're going to flash off this ethanol. Therefore, they're losing product. You're not losing a significant amount. You're not losing anything really tangible. Additionally, the amount of alcohol, this low level of alcohol is probably stabilized inside of your water. So you're probably not going to be losing really anything. You might be losing 0.05%. Not anything really to worry about. Now, when it came to the gravity change during kettle sours, with the same experiment with 16 different lactose strains, we saw no more than a 1 degree Plato or 0.004 degree SG drop across the board. Now, you're going to see this data set come up a lot. You'll notice we have 4 different temperatures here, 30, 35, 40, and 45. A lot of the data we're talking about today is going to be coming from these experiments that we've run internally. You can see here we didn't see anything higher than 1 degree Plato. We're not seeing a big decrease in gravity. So even though we are consuming lactic acid and things like that, we're not losing a lot of alcohol, really almost anything. And one other unique thing to bring up, and this is something that you see some kind of controversy online a little bit, which is why I want to help clarify this. These heterolactic strains are also able to produce small amounts of CO2, but we're not seeing large Saccharomyces levels of CO2 being produced. It's a very small amount of CO2. Now, it's not typically going to cause anything more than a light fizz or spritz. Every now and then online, you'll see photos like this, where this is a brewery that has done a kettle sour in their kettle, and then they turn the kettle on, it starts boiling after the souring, and it looks like it looks like an active beer fermentation. This is not what it's supposed to look like. What you see here is a Saccharomyces contamination of the lactobacillus. And that is a serious problem you see when it comes to kettle sours. And we'll talk about this near the end of today, but making sure, much like for a Saccharomyces, you want to make sure that Saccharomyces culture isn't contaminated with anything else. You don't want lacto, you don't want pedio, acetobacter, Brettanomyces inside that culture. Same thing goes with lacto, but you don't want anything other than lacto in that culture. Breweries have yeast everywhere. It's on the walls, it's in the floor, it's in the air, it's everywhere. When you're making a kettle sour, you need to make sure you do not have a yeast cross-contamination, which might sound a little bit weird, but it's very important to make sure you don't have that cross-contamination. Otherwise, you will be losing ethanol. You will be boiling that off, and that's where you start getting into some problems. Now, Lactobacillus it does have some interactions with oxygen. Lactobacillus is what we would call an anaerobic organism. It prefers to be it prefers the absence of oxygen. Now, many Lactobacillus strains will produce low levels of acetic acid, vinegar, which has a negative impact on Saccharomyces cerevisiae fermentations. There seems to be a light correlation, we'll see the data in a few slides, with DO content, so dissolved oxygen content, where the more DO we see, the increased acetic acid. However, this is very much so strain dependent. You can see right here, this is acetic acid concentrations across 16 different strains. Some strains produce a good amount, and it is temperature dependent. A lot of strains don't produce any acetic acid. And we then start layering on DO content. We do see a slight increase in acetic acid content with DO, but it's not a huge amount. It's not mass. It's not a significant amount for this, but we do see some increase. You may be wondering why we're bringing this up, and this is one to kind of give you the preamble for our interest in Lactobacillus. This is kind of poignant for us. We started doing a lot of research on Lactobacillus because we had a client who was doing kettle sours, and we had no idea why. We didn't understand why, but they were having these fermentations that were just stalling. They weren't fermenting. They were doing the same thing for a long period of time, and the fermentation started getting, where normally they see 80% attenuation, they were only seeing 70, then 60, then 40, then it wouldn't even start. And we were scratching our heads trying to figure out what is going on. We had no idea. We started looking at the acetic acid content, and it was a dead ringer. The higher the acetic acid content, the less fermentation we saw occur inside this beer. And we have further data to back this up. What you see here is it's on the small end of this, but we see acetic acid concentration in ppms and final gravity. There's a strong correlation that the higher the acetic acid content is, the less attenuation we're going to see. And if you push this further, you very quickly get to the point where you're having 50% attenuation or worse. Certain strains are going to produce a lot more. Certain conditions are going to accelerate more. You don't want to get yourself in this position, but we'll talk more about this in a few slides. We want to cover some of the other background information for it first. Now, there are some ideal temperatures for Lactobacillus, and what we see here is that exact data. So we have 4 different temperatures here. We have 30, 35, 40, and 45. And it's pretty clear to see here. You see the light green line, that 35 degrees C is the temperature where most Lactobacillus strains are the happiest. We see the fastest pH decrease. We see the best effect, essentially, brewery conditions at this temperature. This is why we always recommend a brewery's kettle sour at 35 degrees Celsius or 95 degrees Fahrenheit. This is the temperature that works the most consistently, works the quickest, works the most rapidly. So there's a lot of literature out there saying 40 or even 45. And I think the first time I gave a presentation on kettle sour, I was saying 40 or 45 because that's what the common knowledge was. But from all the data we've looked at, beer conditions Lactobacillus in beer seems to work best at around 35 degrees Celsius. So that's what we recommend. And finally, Lactobacillus does have a lot of flavor contributions to bring to the table. Not all lactose tastes the same. A lot of people think that lacto tastes like just clean sour, that's it. But that's not the case at all, and that really does a disservice. We developed LactoBlend 2.0, which if you want to see more information, we have a whole webinar that did about developing that blend. It's developed to have be easier to use and to have kind of a guava orchard fruit tone. Lactobacillus plantarum, this is always a subspecies thing, but for the most part, it's known to be quite lemony. Lactobacillus brevis, I would often describe as kind of a sharp and a bit more spicy. And Delbrueckii tends to be kind of smooth and a bit more muted. Different lactose strains are going to have different other secondary flavors. It's not just sour. They actually have some flavor compounds that can be very beneficial. Don't discredit them. Don't always just go for performance. Say how low can it go and how quickly. Not all lactose are the same. We have to look at strain selection, total acid, flavor compounds, DO, temperature, process optimization, the whole shebang. Much like we'd think about Saccharomyces, we have to think about lacto under similar terms. So with that kind of quick preamble on lacto, we're going to jump into how we can actually control these quick sours. Because a lot of, you probably guessed already, or if you didn't know already, there's a lot of levers, a lot of things we can manipulate to help increase or decrease the quality of these beers. A lot of things we can do to help make these beers more consistent. So now that we understand the basics, we can now start breaking these things down. So we're going to actually break down boiling of the wort to sanitize it, cooling of your wort, inoculation, and the reboil. So for boiling, this might seem very kind of nitty-gritty or kind of esoteric in a sense, but it actually has a big impact. Boiling the wort for full duration, you're standing kind of 60 to 90 minutes that you'd see for a pale ale and IPA pills or things like that. You still want to do it when you're making these styles of beer because you still need to flash off unwanted compounds, kind of cereal grainy characteristics that are undesirable. Even DMS is a big one. So when you start looking at this, you kind of see two schools of thought really start to form, and that is to boil before or to boil after you sour. I always recommend as a minimum, to boil for at least 45 minutes, and this is the important bit, before you sour. And I know some people are going to disagree with this, but this is the reason why we recommend it. So boiling hard before you sour has a few main benefits. The first one, because as we alluded to beforehand, has to do with acetic acid content. Now, we do know that acetic acid and DO are correlated. How tightly, we're not quite sure. But boiling the wort hard is going to remove off a lot of these flavor compounds, or remove a lot of DO that can then turn into negative flavor compounds. Bubbling CO2 through a wort to try and flash off DO doesn't really quite work, but boiling absolutely does. So if you want to try and make sure you keep as anaerobic environment as possible, boiling your wort for the full duration before you sour has a big impact. Now, the second portion I added here, and this is anecdotal. There's not a lot of information on this, but if you want to find more, I'd recommend you go to our Escarpment Day 2 video on THP. The mouse in the room, I believe, is what it's called. Lactobacillus is known, and there's research that's been shown that it does produce THP, which is this kind of mousy characteristic, usually considered to be a fault in most beers. This is mainly caused by lysine consumption and other kind of other protein-based consumptions with lactobacillus. So the theory here, and we've seen this play out in breweries, but there's no research on it, so this is strictly anecdotal, is that by boiling more aggressively before the wort, you're going to see some of these precursors, mainly proteins and amino acids, come out as trub in your hot and cold break. So by removing the amount of precursors present by boiling, we're going to be producing less of the end byproduct because we gave it less precursors to begin with. That's the core concept behind boiling hard to begin with. Now, what's not mentioned in the slides is there's also a handful of different fatty acids, different other flavor compounds that through bioconversion, which we talked about and we've had other lectures on, lactobacillus can turn those flavor compounds into other flavor compounds that may not be desired, may not even be intentional. By boiling hard beforehand, you're more likely to get a cleaner, smoother, souring in these beers, less muddied, less kind of complicated, so to speak. That can be a very good thing. So for these reasons, if you're looking for kind of a clean, crisp type of kettle sour, we're going to be recommending that you do a full duration boil before you start souring to help kind of clear up a lot of these precursors so you don't have these kind of muddiness inside of your beer. The next thing you see the brewery then do is cool their wort down to 35 degrees Celsius. And this can be kind of tricky because at face value, it seems mechanically just complicated. How most breweries do this is by hooking up their normal cool out hex, circulate their wort in their, go from kettle heat exchanger, where you then normally go to your fermenter. They'll often then recirculate that back into their kettle. So you're circulating your wort around while cooling it. That's the most common way to do it, especially if you're doing the classic kind of kettle sour, the souring occurring inside of your kettle. However, many breweries are moving towards a dedicated kind of souring tank or souring inside their fermenter. And if that's the case, this becomes very easy. You're simply casting out your wort as you would normal, but instead of going at, say, 18 or 20 degrees Celsius, going to 35. That's it. You're just casting it warm. That's all you're doing. Now, for the first method where you're souring inside of your kettle, it just looks like this. So the wort inside of your kettle will then go to your heat exchanger. There'll be a pump here at first. This will then go through. Usually there's a CO2 stone, so you're bubbling little bits of CO2 through it to make sure you don't pull a vacuum and don't pull more oxygen in, at which point it then gets recirculated, so it gets sent back to the kettle, and this recirculates. You can bring your kettle from 100 degrees C down to 35. Takes a while, but it does work. Next step for this is, once we have our soured wort, is to pitch a lactobacillus culture into that liquid. Now, most labs, including us, we sell a lot of lactobacillus. We sell ready-to-pitch lactobacillus into your kettle for whatever size volume, whatever size of brew you need. Now, using fresh culture it's going to be very effective. It's going to be very efficient, but it's expensive. I understand that. We're not a. We understand you have to reuse cultures as many times as possible. We do the same thing. I did the same thing when I was brewing. This leads to the obvious question of, can I reuse my lactoculture? And the answer to this is an absolutely resounding, absolutely. You should be. I would recommend you reuse your culture. So how do you do it? So many breweries so when you're looking at harvested, the common mechanism, common methodologies as such. At the end of your sour, so once you got it down to about 3 to 3.5 or so, you're going to pull off usually about 20 to 50 liters per 10 hectoliters of volume off that batch. So it's not boiled yet. It's fully soured. It's near the end. You're going to start pulling off some samples, some of that liquid into some sterile kegs. This is the important bit, sterile. If you have, if these kegs previously had unfiltered beer in them, or even if you had unfiltered beer that then went through your keg washer, the keg washer in many cases can be a vector for contamination where the rinse water or even the caustic can contain live lactobacillus cells from previous kegs. You'd be amazed what can get inside these systems. If you want to take 20 to 50 liters per 10 hectoliter batch in sterile vessels, and you want to transfer some of this kettled sour liquid into those tanks. Once you have them transferred, seal them up, keep them nice and cold, put them in your cold room, and then use them as soon as possible, just like you would a yeast culture. Now, when you're then making the next batch, all you have to do is pressurize these kegs and inject that initial lactobacillus culture from your last batch into the next brew. Now, you can go as low as 2%, or about 20 liters of liquid per 10 hectoliter batch. This is not a lot. It will typically cause it will cause an elongation of lag time, so you'll see slower souring inside that vessel. For this reason, most breweries will go to about 5%, about 50 liters per 10 hex. That's a pretty consistent number. You do also see some breweries go even higher, where they have 10%, where for every 10 hex of wort in the kettle, they're knocking out 2 50-liter kegs inside that brew. Might be a little over, might not be needed. There's reasons to do it, which we'll talk about in a bit, but that's kind of 5% is pretty normal. 1 50-liter keg per 10 hex is pretty standard. So we now have a tank full of, either a fermenter or a kettle full of souring liquid. When is it done? That's the next logical question. How do we tell when it is done? When do we stop it? There are some issues with it going too far, which I will talk about at the end of the presentation. So it's not just, once it's stable pH. Stable pH can actually have some negative repercussions. We're going to talk about when you should cut this. Now, how long you should boil your wort for is pretty easy. Assuming that you boiled this wort hard beforehand for 60 minutes, you're just looking to sanitize it at this point. If you didn't, and you only did say a 5 to 10 minute boil, you want to boil this thing hard. You want to boil it for 60 minutes just so you want to flash off that DMS, flash off these compounds that you don't want. Figuring out when it's done is a bit more complicated. And to understand this, we kind of have to I'm trying to summarize a topic here that is very complicated. So if people have more questions, but we can talk about this at the end. But we have to figure out the difference between titratable acidity and pH. So TA versus pH. And this is an important thing for us to factor in, because the human palate doesn't actually taste pH. When we think orange juice or things, that we think things are sour, but that's not actually what we're tasting. We're actually tasting the molecules of acid, which is described as TA. So to kind of illustrate this, I have a little example you see at the bottom. So here we have the same beer produced with 2 different water profiles. So we have an IPA and a Berliner Weiss. So for the IPA, the pH for the first one is 4.3. TA is only 4.5 and it has almost no tartness to it, which it shouldn't. There's almost no acid present. However, for IPA 2, which is brewed with somewhere that has quite hard water, say a Guelph analog, the pH is a bit lower. And the tartness, the TA is much higher. In order for us to kind of knock this pH down, we have to add a lot more acid. In this case, about 5 times the amount of acid, to the point where we actually get a light acidity. If we look at the Berliner Weiss, this is where we start getting some significant impacts here. So if I make a Berliner Weiss essentially with distilled water, think Pilsen, or even say BC or Victoria, BC, very soft water. I can make a Berliner Weiss, and that wort's going to get down to pH 3.3. And because there's almost no minerality present, any acid I add is going to change the pH radically. It's going to have a big impact on that pH. And I can have a beer that's pH 3.3, but it's not going to taste very tart. It's going to be lightly tart. However, if I then say make the same beer and I hit the same pH 3.3, but I brewed in Guelph, we have a lot of alkalinity, a lot of minerality. I'm going to have to add a lot more acid in order to eat through all that buffering capacity to get to pH 3.3. And the end result here is, even though the pHs are the same, that beer made in the hard water is going to be much more acidic. It's going to taste much more acidic because there's many more molecules of acid inside that water. It's going to be very tart. And that's the important bit here, understanding the difference between these two. Now, a pH meter, which is what most breweries have, it's not going to work for this, not on its own. You can't say always just shoot for pH 3.3 because you're losing the TA portion to this. Whether or not you have hard water, soft water, and even what season it is. What we often see is that in the summer, the water hardness goes up because solubility of these minerals increases with temperature. And in the winter, we see the solubility of these minerals go down because solubility of minerals decreases with colder temperatures. So if the pH isn't really what you want, what you're looking for is TA, titratable acidity, and that's a conversation for a different point. What I'd recommend you do is, to use kind of the best of both worlds. Record your pH, but also taste. Also taste it. It doesn't have to be fancy for it to be effective. Tasting the kettle sour to see when it's come along or when it's ready to start cooking it is probably the best thing you can do. At least that's how I'd recommend, unless you have the equipment to do a TA test. So with that kind of the basics out of the way, we're going to start going into some kind of common problems and techniques you see some brewers implement and kind of explain why they occur or why you would want to implement them. The problems we're going to talk about are residual IBUs inhibiting souring, stratification of souring, high acetic acid inhibiting Saccharomyces fermentation, which we talked about briefly already, and some common techniques being the pre-acidification of the wort, bubbling of CO2 throughout it, and halting the souring with dry hopping. Something you're seeing becoming much more common. So residual IBUs inhibiting souring is probably the #1 issue we see with kettle sours. And it makes a lot of sense when you start looking at it. And I feel like I've had people on emails who, after I sent the email, they've read it and then kind of facepalm themselves going, I should have known this. What happens here is that when you say brew an IPA or a pale ale, anything that really has hops in it, if you don't caustic rinse the system, even sometimes if you do, you might have bits of hop debris present in your heat exchanger. Things get through, it just traps. Again, it's unless you take it apart, it's really hard to get rid of them. You're going to have little bits of hops present. Now, what's going to happen is if I then say take water inside that system and I boil the water inside this kettle or this area where I previously had hops, I'm going to be picking up some IBUs via those trace kind of debris of hops. Because hops don't release all of their IBUs when you boil them. They actually release very few of them. The isomerization rate's like 35% tops. So what can happen for a lot of these issues is that brewers are thinking they're not adding any hops to that beer, but they actually end up producing like 5 to 10 IBUs in that beer just due to residual hops inside the system. That can be a problem, especially if you have dead legs or things like that inside your system. Ports on your boil kettle that just are hard to clean. This can be a serious problem. Now the solution here is pretty easy. It's just a caustic clean it. Caustic because it's alkaline, because it's basic. We see isomerization of hops increase radically when we make things more alkaline, which is why caustic's so good. We caustic rinse the entire system. We see the isomerization rate of any trapped residual hops inside the system skyrocket into about 100. All the IBUs from that green material is extracted. So even when we rinse the entire system, if we still have some entrapped hop material, that entrapped hop material does not have IBUs. It's gone, it's depleted. So when we then make our kettle sour on top of it, we don't have any issues. All the IBUs for any sort of debris we have in the system are gone. And again, this might seem really basic, but this is probably the #1 cause of issues we see breweries have who are trying to make kettle sours for the first time. This is absolutely the #1 thing. What I'd recommend you do if you're trying to make a kettle, or if you're making a kettle sour, you need to caustic clean your system before you do it. You should never make a kettle sour after you make your IPA, unless you put a caustic rinse between those two. Simply just rinsing the kettle out isn't going to cut it. Caustic rinse the whole system, or caustic wash the whole system. Otherwise, you're leaving yourself open to a lot of risk. Stratification of souring is something that we see some breweries have problems with, and it's usually kind of the same idea where it's a frantic email saying it's not working, and then, oh, it is working. This has a much more of an issue when we start looking at the homolactic fermentation strains, where they're not producing any sort of CO2, and when you see breweries who aren't bubbling CO2 throughout the entire vessel. Oftentimes, people will take a sample from the top of their kettle. Lactobacillus preferring anaerobic environment stays at the bottom of the kettle. Therefore, the acid production is going to occur more localized at the bottom. And what you end up seeing is the bottom's very sour, the top's not souring yet. Someone takes a sample from the top, freaks out, saying it's not working. The solution here is just to make sure you take a sample throughout the entire thing. Make sure you see the bottom is oftentimes the bottom is souring, but the top isn't. And that's just due to stratification of the souring. What you can do is just add some CO2 bubbles to go through the entire thing, help things nice and kind of mix and become uniform. Knock down some more DO, help to prevent diffusion, things like that. It helps quite a lot. Make sure you know where you're sampling from, because Lactobacillus is going to have this problem. And then this last one is not common, but I really want to make sure we stress this, because this is a problem, and it can be a big issue. So some lactocultures, as we've mentioned so far, and this is again mainly strain dependent, produce high levels of acetic acid. Now, anecdotally, we have seen this get to high levels when we start seeing breweries kettle sour at those higher temperatures, 45 degrees Celsius, 113 degrees Fahrenheit, that high end. We recommend 35 degrees Celsius, so you don't go anywhere near this. And when you start using a smaller inoculation rate, this is anecdotal, you start seeing higher concentrations, or we have seen higher concentrations of acetic acid being produced. But the end result of this can be, if you get into the scenario you're doing, and the situation at hand was they're doing kettle sour after kettle sour after kettle sour. This culture was never essentially stopping souring, and it was just producing more and more and more and more acetate. More acetic acid. This brewery essentially shut down for a bit, because not shut down overall, but they couldn't produce beer, because they couldn't produce sour beer, because everything was just becoming unfermentable due to the too high level of acetic acid. And to give you an idea of the perception of acetic acid, you wouldn't smell the beer and think, oh, that's vinegar, or oh, that's malt vinegar, or anything like that. It was very subtle. It wasn't aggressive. You wouldn't almost detect it on the human palate unless you're a bit more sensitive to it. It was just a higher level of acetic acid than what Saccharomyces is capable of handling. Now, again, all things are strain dependent. Some Saccharomyces strains have no issue handling it. They'll just laugh at it. Saisons in particular have no issue with it, or they have a higher tolerance. But things like Cali or English ales, I believe English ales, they're sensitive to it. They're not as able to handle this stressor, so you have to be worried about it. So yeah, we recommend 35 degrees C. We recommend using larger inoculation rates at 5 to 10% or so, usually the 5. We recommend boiling for longer periods, really drive off that DO, so we see even less CO2, so even less acetic acid, and bubbling CO2, so you stop stratification and you help knock these things down. What are the problems? When it comes to kind of standard techniques, we're going to look at a few. So pre-acidification is very, very common. But the main question you see some breweries do is just, why would I do this? You're starting to see some breweries kind of steer away from it. Now, the reason for it is that unhopped wort is a playground for pathogenic organisms to grow. And pathogenic organisms are things that are harmful to us, being humans. These are things that can cause serious problems. Things like E. coli, Clostridium botulinum, the thing that produces botulotoxin, Staphylococcus aureus, all of these kind of nasty things that can actually send you to the hospital. These can all survive above pH 4. The higher the pH is, the faster they're gonna take hold and start fermenting. So the idea here is that by pre-acidifying your wort to at least pH 4.5, I'd probably go a bit lower, but pH 4.5 is kind of the high end. You're gonna help prevent these organisms from growing. Here's the same chart we saw earlier, and we can look right here that around pH 4.5. E. coli right at the end of it, salmonella, usually a little bit less deadly when it comes to these things. Most of these organisms are toast. You go with 4.2, E. coli, salmonella, they're pretty much all toast. If we pre-acidify our wort to this point, it means that we don't have to worry about all this pathogenicity inside of our wort. If we have an issue with lactobacillus where we have a 24-hour lag period, we know we're going to be fine. Now, you shouldn't have a 24-hour lag phase. That's a technique issue and a cell health issue, but that's a separate conversation. Pre-acidifying does help quite significantly. Help stabilize your beer. Now, there's also some other benefits, and this is strictly anecdotal, but I want to thank Mark Horsley for this. He's the one who did this and posted the picture to the Milk the Funk wiki if you want to find it there. Pre-acidification has been shown to improve head retention in kettle sours. Now, there's some contention around this, but it's pretty stable. Well, you see here on the right hand side is I have those backwards. The left has a pH starting at 5.3, and the right has a pH starting at 4.7. The one that was pre-acidified had greater head retention. That's backwards. What we believe is happening here is that the lower pHs is actually inhibiting lactobacillus from producing a protease, or an enzyme that's going to break down foam-positive proteins. There's some literature to back this statement up, so it makes a lot of sense. How do you pre-acidify? It's pretty simple. Much like you would say make pH corrections inside of your kettle, inside of your mash tun, or inside of your kettle, you're going to be adding either lactic acid or phosphoric acid to your kettles. That's the standard way to do it. But there's one thing that a lot of brewers don't take into account, and that is the fact that if you're using secondary use culture, you're already doing this. So by adding, say, 5% of your culture back from your first batch into your second batch, you're adding a good amount of lactic acid. You know, that initial batch produced tons of lactic acid already. You're souring it by injecting it into the next batch. That's going to be lowering the pH of that next batch significantly already. If you hit that 5% state point already for your culture, you're going to be pre-acidifying in some cases completely. If you go to the 10%, you're going to be acidifying even more. You know, making sure you kind of hit the middle, the point for this is quite useful. Some breweries do kind of calibrate how much inoculation, or how much culture to add from the last batch, simply based on pre-acidification. It's kind of neat. It's a really kind of intuitive way to do it, where you don't have to worry about adding lactic acid or phosphoric acid. You don't have to get the chemicals out. You're just going to be adding this with your initial cell culture to begin with. Makes life easy. So that's one of the main techniques. Well, the other common techniques you see is by bubbling CO2 through the bottom of the port. Now, this has become kind of a hot button controversial topic, and I'm not sure why. So why do you do it? The first thing is to help maintain low DOs. You know, low DO is going to help make sure we don't get any acetic acid. We haven't talked about this already, but it's also going to likely prevent any sort of fatty acids or other flavor compounds from being oxidized inside that wort. It's going to reduce color pickup. You know, it's beer. We want to reduce DO as much as possible. Especially if you're using homolactic fermentation strains where they're not producing CO2 on their own. We probably want to do this. We want to use a mix. So we want the culture to be mixed throughout the entire fermentation, so we have adequate. So we don't have any stratification, as we saw earlier, and we want to help flash off any sort of unwanted compounds that might be being produced. You know, that turbulence is going to help remove some of these compounds. Now, is this technique needed? Absolutely not. It's simply a nice to have. It is a good thing to do, but it is by no means required. Does it safeguard you against some common problems? Absolutely. This is going to help prevent some common problems we see with these beer styles from occurring. Now, if you're a home brewer, I probably wouldn't do this myself. Doesn't make sense. I would, from my standpoint, I would pressurize the kegs I'm going to be using to kettle sour in, and then come back a few days later and just, you know, go from there. But if you're just using carboys, I would not let this stop you from making kettle sours. You know, this is a reduction in risk. And for the home brewer, yeah, that can be a huge cost to incur simply to have a very, very small increase in potential quality. For the pro brewer, though, tank of CO2 is cheap relative to the amount of beer. If you can increase the quality of the beer you're being produced for the tank of 1 CO2, I think it's a good trade. I'd make that call every single time. It is absolutely, you know, the call of the brewer, but I think this is absolutely a well worth investment for the pro brewer to do from an increased quality and decreased risk standpoint. It's risk mitigation. And this is becoming very common. At one point it was kind of an edge case, but it's becoming less and less so. Lacto is inhibited by IBU. And this important thing to mention here. It's inhibited, not killed. It is killed with heat. It is inhibited by IBU. So what this means is that if I have an inhibited IBU in a beer and I transfer the beer from, say, tank A to tank B, and then I forget to sanitize that line, and I then bring, say, a Helles, a light lager, something that has less than 10 IBUs. The IBUs retained, the lactobacillus retained in that hose is probably then going to reactivate when it's in an environment where it's not inhibited. That's how lactobacillus works. It's a survivalist. It's going to survive. If you're making beers that are just 40 IBUs and above, I wouldn't worry about this. I wouldn't worry. You know, it's going to work really well. And the reason you see some breweries doing this is that it's really easy. It makes your life easier. You don't have to reboil your wort again. You don't have to transfer the wort from multiple vessels. It's really simple. And what you even see some breweries do, instead of using dry hops to sterilize it, they'll say if their fermenter is able to handle 4 worts from their brew house, they'll cast 3 out with 0 IBUs, let it sour, and then cast a 4th wort in at, say, 40 IBUs. So the whole thing, you know, dilutes out to 10 IBUs, and lactobacillus is inhibited. Really easy way to kind of get a consistent, stable product that you don't have to move around. There's also the benefit here that lactobacillus does have some positive elements when it's in packaged product, especially if you have hops present. We've seen this in the lab where inhibited lactobacillus inside of a bottle actually turned rather boring hops into something that was quite beautiful. This is becoming a much more common technique just due to simplicity and kind of ease of use, but it doesn't work for all breweries. If you're making a lot of beers that are below 10 IBUs or are more susceptible to contamination, this probably isn't a technique you want to go with. With that, we're going to kind of wrap this up and go over some new research and kind of advances in these techniques. So the first one is something that's a little bit kind of esoteric out there, and I haven't seen this occur, but there's a lot of literature on it, and I find it honestly fascinating. So bacteriophages are pretty neat. And this is something that can cause lactose cell death. So what is a bacteriophage? Bacteriophage is a virus or organism, we're not going to get into that, that kills bacteria. These phages can build up in facilities that are using the same culture over and over and over and over again. And it would kind of look something like this. Say Gen 1, I have one bacteriophage, which gave me very little cell death. But that one bacteriophage, much like everything, is going to replicate massively. So next gen, I may have 100. So I'm going to see moderate cell death. The gen after that, I have 100,000. And I'm going to see near total cell death, total cell population death. This is a big issue in the dairy industry, especially the cheese industry and things like that, where a bacteriophage can get in because they're using lactobacillus over and over and over and over and over again, usually the same strain. If this gets inside the facility, it wipes out everything. This bacteriophage can get in and then halt all fermentations. I have not seen this in breweries. And a more accurate statement is I have not been aware I have seen this in a brewery. It's possible that we've seen this and we just weren't testing for bacteriophages. This is something that the beer industry has had to worry about. But I wouldn't be surprised if this eventually does kind of rear its head in our industry. Just something that was kind of really unique, and I thought it'd be kind of fun to share. Other thing for this is off flavors and kettle sours. This is something that I didn't know where else to put it, honestly, so I wanted to put it in here. Many off flavors and kettle sours are based on unhealthy cell cultures. Much like yeast, the healthier your bacterial culture is, the better your beer is going to be. If you leave your bacterial culture in the fridge for 2 months, it's going to be angry. Much like if you leave your Saccharomyces culture in the fridge for 2 months, it's going to be angry. You can do things to help bring the culture back to life, get the culture healthy, and then use it inside of your facility. Don't hurt them. Don't be mean to them. Your beer will thank you. And finally, this is something that's kind of neat, and I think it's a good place for us to end, is something that we've been calling the lab infinite improbability drive. It's a little bit of a Hitchhiker's Guide to the Galaxy reference there. If anyone hasn't read that, I'd recommend you do so. And it kind of follows this principle. So kettle sour ideal temps around 35 degrees Celsius. Kveik's ideal temperature is also around 35 degrees Celsius. So what you do is you make a 0 IBU wort and you inoculate it with both lacto and Kveik at the same time. It's a great part. So you have fermentation and you have souring occur at the same time. When the desired level of sourness is achieved, add your dry hops, or you can even add things like hexa hops, like a pre-isomerized hops or things like that. The result here is that you often Kveik fermenting very quickly within 36 to 48 hours. You can often have a drinkable dry hop sour in 3 to 4 days. It's crazy. Works phenomenally well. We did a lot of this in the lab a few summers back, and it was absolutely delightful. I'd recommend you try it if you haven't done so already. It works very, very well. And if you want to learn more about all this stuff, this is a few on April 14th. This is 2 months ago. We did our former employee is Neto. She did a whole presentation about the road to Lacto 2.0. If you want to learn more about lactobacillus or kind of more of the research we did in there, you can go watch that presentation. It's currently posted on YouTube. It's a wonderful time if you really want to dive in a bit deeper into this stuff. And with that, that is all we have for today. I hope everyone kind of got a little bit of useful information out of that, and I think we'll start digging into some questions with that.
Alrighty, thanks, Nate. Informative as always. Glad you gave a little shout out to the infinite improbability drive, both the literary device and Hitchhiker's Guide to the Galaxy, and the beer that is able to cross hyperspace in a nothing of a second. Good stuff. It's a lot of fun. I was trying to
figure out how we put a bowl of petunias in there, and but I couldn't quite figure that out.
Yeah. we have a few questions here. So we're going to go, as always, sort of in order of the votes.
Yep.
So the first one, and I think you actually kind of did cover this pretty much right at the end, was co-pitching lacto and kvike at warm temperatures without pre-boiling. And then also, what are the, but maybe more relevant, what are the pros and cons of dry hopping at those warm temperatures?
Oh, okay. So there's a few layers of questions in here.
Mm-hmm.
The first one I'd recommend, I want to tackle there is the without boiling part. I would still recommend for this beer that you boil a full duration before you sour. That has a lot to do with fatty acid flash off and things like that. Mm-hmm. But yeah, it absolutely works. It works really well. Now, I can't stress this part enough, though. It's risky under a lot of commercial breweries. Like if you are making a elbow bender golden lager, I would not recommend you do this, because you're going to put your kettle sour, so you're going to put your infinite probability drive analog inside your canning line, and then you're going to put your golden Helles or your American light lager through it, and your entire American light lager could become light sour beers. Mm-hmm. This is years and years and years ago, but a brewery that we originally kind of got our start out of, they had a whole batch of beer that this happened to, and then they sold it a few years later. I think it was called sourdough, like dough, like Homer. It happens. Like it's more pervasive than you probably expected, or than most people would expect. I have a hard time saying that everyone should do this.
Mm-hmm. It's one of those things. I'm not sure if you didn't quite cover. You covered the potential issues with bacteriophages, but one of the other kind of interesting things is that Lactobacillus seem to be even among bacteria really good at passing around genetic material between each other. So even though most of the lactose that are used, produced by yeast labs are hop sensitive, they don't have that hop resistance. It is known that hop resistance genetic information can kind of just be passed around like like coins by lactose to each other. So it is possible, and that is why there is always a risk with live lacto going through packaging lines and stuff like that.
I meant to bring this up also earlier. The stuff on bacteriophages I found really fascinating, and I don't think this is time and place to kind of go into it, but the individual who showed me about this stuff, his name's Andrew Turner. I think he did a presentation on kettle souring. I want to say it was a conference a while ago. I can't recall where. But he has a lot of information. I don't know if he's here, but it's that
was the one a couple years ago, right?
Yeah.
Yeah. Okay.
Yeah, it's rather neat.
Cool.
Yeah.
Okay. Our next question: what are your thoughts on doing a kettle sour then pitching Brett as the only yeast?
That's kind of a you question. I think that's fascinating. And my gut reaction is the information that Chad Jacobson showed in his undergrad. Sorry, in his PhD, master's Contaminants project.
Yeah.
Where he showed that about 1,000 milligrams, I think it was, about 1 to 3 grams per liter of lactic acid inside a solution actually accelerated 100% Brett fermentations. So my gut reaction on that is to go for it. But I believe he also showed that if you added too much, it would start to inhibit them, and you saw a decrease in attenuation. So I think there's a degree of severity here.
There's definitely flavor consequences too. Yeah, we see Andrew Turner is here. Great.
Yeah, cool.
There's flavor consequences. Like I think I don't have it in front of me, but I've definitely read the thing a few times. If I recall, in those lactic acid pre-acidified beers, there's obviously more ethyl lactate, like the coconutty kind of flavor, but less of some of the other Brett aroma compounds. So there's like a trade-off. I think it's a good idea. Try it out. I don't have a ton of experience with fermenting kettle sours with Brettanomyces only. I've done a lot with like either kettle sours or sort of sequential ferments, sort of in the Berliner side where there's Saccharomyces and Brett, and I really love that. Yeah, I would say like purebred with a kettle sour wort, you're going to get a lot of that ethyl lactate, so like a lot of that sort of coconutty flavor, and maybe not as much of the sort of expected Brett characteristics.
Yeah, I would, to kind of reiterate something I said beforehand, but I think your water is going to play a huge impact on this, because if you kettle sour, you say kind of like if you had super soft water versus hard water, the milligrams, the ppms of lactic acid you're going to have inside that wort are going to be very different, and that's going to have a bigger impact on. I would assume it's going to have a bigger impact on 100% Brettanomyces fermentations than anything else, because all organisms are kind of governed by both.
Yeah,
it's not just one.
Yeah, it's still an enigma. I'm running an experiment right now on a Brett primary idea, just honestly based on someone that followed up after one of our webinars with a great idea, and the results are negative. But that's science, right?
Yep.
We can cross that one off the list as well. But yeah, that's remains a perpetual challenge, speeding up the Brett primary ferment.
Yep, that was really cool.
Next question. You mentioned that caustics are required to clean after an IPA before kettle souring. Are there any other interactions between residual ingredients, between any brew styles like this, that would require caustic cleaning in between?
Not that I know of, but caustic cleaning in between is always a good idea. I know it's not always practical. That's a whole other thing.
Okay.
But I can't think of one, unless you're using fruits or you're using kind of things like that. I can't think of a scenario where we'd be seeing huge variations.
Yeah.
Like IBUs inhibit the organism, so it's going to govern it. It's going to have a big impact.
Yeah, there's two things that I would add here, just based on personal experience. Oils from different plants. So citrus oils, very antimicrobial, can cause problems, and I don't know how to describe this, coniferous plant oils as well. Juniper, pine, having made a few of the traditional Norwegian beers and ended up with a bunch of really sticky juniper residue on the sides of the kettle. That was
I remember
that can be an issue. It is antimicrobial as well.
I remember seeing
those are pretty obscure cases, I guess.
Yeah, anything that's going to have a high oil content is going to cause problems.
Yeah.
But for all those things, if it has a high oil, caustic's going to break it all down. Literally, it's going to saponify it, and it's going to get removed.
Yeah, I will say like this, it's less of an issue on the homebrew side. But the advantage with homebrewing is that you can get in and physically scrub everything. That's a lot harder to do with a big brew house. So
yeah, it doesn't work with a big brew house.
Yeah. What is the recommended pitching rate for lacto, and does it depend on the original gravity?
Okay, first off, yes, it does depend on. I would say it does depend on original gravity, because you're asking how much souring for it to actually occur. Pitching rate for lacto is difficult because it moves. It's I can't count you if you're all moving around. It's from a movie, I think. It's very difficult to actually count it. So what we do, and you can do CFU plates and things like that. It does work, but it's very time consuming, and you get the data several days later, so it's not really practical. Consistent technique is usually the most common, and that's where you see most breweries kind of go forth. We sell, Richard, correct me on this, but I think it's 1 liter per 10 hec of our culture.
Double that, but yeah.
Okay, 2 liters per 10 hec.
2 liters is a 10 hec pitch, yeah.
I haven't made that in a very long time.
I know.
That's okay. But when we grow it with enriched medias and things like that, so it's getting to a much higher density than it would be when you get it in your kettle. So when you're cropping this from your tank, you're getting it at a much lower density than what we are supplying it to you. And it's not just us; other labs are the same way. You're going to you are physically going to be harvesting a lower cell count per liter, not necessarily total, that you get from us. Now, when you then go to use use it in the next subsequent batch, I would recommend, much like yeast cell pitch rate, shoot to overpitch, and the negative consequences of overpitching are far less than the negative consequences of underpitching. Like if you underpitch, your chance of getting off flavors, much like fermentation, standard yeast fermentation, is going to be higher. You're going to see an increase in lag phase. You're going to see an increase in all these kind of negative elements that we'd see inside these beers. Pitch more than you think you need. It's going to make your life easier. And again, if you pitch, like that's why you see some breweries go to the 10% rule, which might seem crazy. But it works, and you're pre-acidifying and inoculating a single shot, which works great. And one other thing to keep in mind here is that just from a kind of a numbers standpoint, you're not losing wort. That's kind of seems to be the biggest pushback people have by doing 10% or even 5%. Is that, well, I'm losing that batch. Like, no, you're just adding to the next batch. Like, yes, your initial kettle sour, say if it's 10 hex, is now only 950 liters, 9.5 hex. But the next kettle sour you do is going to be 10, and then you're going to throw 10.5 hex. You're going to pull half a heck off, and then you're going to keep on cycling this through. So you're not losing the beer. I've always found that as being the kind of the main resistance point. So I just wanted to address it.
Yeah, for sure. The only thing I would add here is that the lactocultures that we're supplying, they're actually at pretty much the same density as the yeast. They don't look as thick or like pancake battery, but that's just because the lactose cells are so much smaller. But we can get those cultures to really high densities, without having to like concentrate them or anything, it's a lot of fun.
Science.
Yeah. Saw some votes go up and down for a sec.
Market will be available for it'll be present on YouTube. We still have to figure out the presentation links and things like that. That's one of the things we're going to be doing before season 2 starts.
Yeah. Are there any Kvike strains you would recommend not using for co-pitched sours?
My reflex is, so the thing I immediately want to say is crispy, but I have no evidence behind that.
Yeah, it would just be clean.
Yeah.
Depends what you're after, right? I know, like in general, Ebegarden is not quite as stress resistant as most Kvikes. That being said, I've had good results. I've tasted good results, with Ebegarden in quick sours as well.
All right.
Ebegarden and Lacto 2, you can, really, really sort of amplify that guava thing. So, your mileage may vary, but it can work. Would taking a gravity reading tell you when souring is done?
No. Rich and I were chatting about this before it started, and this is very, I don't want to say contested, but it's there's a lot of anecdotal evidence pointing towards this, but there's no research on it. So keep this in mind. The longer kettle sour goes, the more acetate byproducts we see, which could theoretically result in more acetic acid. I have that right?
Yeah, it's possible.
Yeah.
We need a brewery willing to let us, I guess, maybe sample a tank for a couple of weeks.
Yeah. The reason I bring that up is because the gravity reading is going to probably keep on going down as that occurs, because acetic acid is less dense than sugar. So I don't know how, the time it requires to get a stable gravity read is probably going to be difficult. You're going to see different amounts of sourness occur. Like you're looking at like 0.00 SG. So nothing that you could measure with a hydrometer or a refract. You need to have a densitometer. You need to have something that has much more accurate. You're looking for kind of scientific level apparatuses in order to actually pull that off. And even then, you're not going to get a high degree of resolution on it. And you don't know whether or not you're entering into that acetic portion to it, or whether or not what you're looking at is just lactic acid. One thing I didn't put in the slides is because this is kind of getting down the nitty gritty for it. Lactic acid is more dense than ethanol, which means that like we lose less than 1 degree Plato which is what we typically see for a kettle sour. that doesn't mean that you've lost 1 degree Plato to the ether. It means that you've turned sugars into a less dense substance than sugar, but still more dense than ethanol. So you've probably lost, say you lose 1 degree Plato, just to keep the math simple, you've probably lost 1.5 degrees Plato of fermentable substance because it's been turned into lactic acid or something like that. Like even when you see kettle sours, doing a simple OG to FG gravity reading to try and determine alcohol content, it's not very accurate. Using things like an alkalizer is recommended for those things.
Yeah, we found that getting a truly accurate alcohol measurement with kettle sours really required HPLC. But yeah, I mean, something like an alkalizer will work in a pinch too. But yeah, just because some of that sugar gets turned into acids, oftentimes if you just type in OG and FG, you're probably over predicting the amount of alcohol in that beer.
And some people get kind of freaked out because they'll do a kettle sour and their beer, for what a standard beer would be, under attenuates. But it's because a lot of the things that are left over at the end of it are actually lactic acid, which is more dense than ethanol. There's that weird kind of, some strains are said to have an increased attenuation rate in the presence of lactic acid. And I can't help but think that these two kind of balance each other out a little bit if it's present or if that's true. But that's really entering like the scary unresearched area of the beer community.
Yeah, absolutely. Another question. I think this is actually a really good one because there's maybe some myth busting that can be done here. When using lactose in a kettle sour, would you recommend adding the lactose to the kettle prior to souring or after? And I will ask, the question also, Nate. Does lacto prefer lactose, or would it rather consume glucose and fructose?
It would. I would think that it would prefer glucose and fructose, despite the lac prefix in both of them.
Everything does, yeah.
Yeah, everything does.
But they have the enzymes, right?
Yeah, exactly. They just because you can do something doesn't mean you're going to or you should. From a practical standpoint, I would recommend that you add, assuming that you're doing a standard kettle sour where you're boiling it after the souring phase, I would recommend you add the lactose at that point. And that's just a practical thing. You have to boil lactose powder in order to get it in solution and easily get it into solution. So you have to have heat. So if you're doing the dry hop or hexa addition at the end of fermentation in order to stall fermentation, then you have to add it before souring. I just wouldn't want to have high amounts of high amounts of lactose and lactobacillus being present, just because I would, why muddy things when you don't need to muddy things? Why throw different carbohydrates at lacto when you don't need to? That may be kind of redundant or not required or not impactful, but that's just kind of my reasonings.
Yeah, I don't know. I haven't played it. Like anytime that I've added lactose, we've kind of just like boiled up a lactose solution and cooled it down, like boiling to get rid of the DO. Cooled it down and added it, basically at the same time as kegging the beer.
Yep.
Or packaging the beer, right? The equivalent on the pro side.
Yeah, whenever my students want to do kettle sours with lactose, I always recommend second boil, and they've always turned out. So that's kind of my experience on it.
All right, I think that's about it for our questions.
There's one question here I wanted to just kind of briefly mention. This is from Luke Van Oort, saying you wanted to increase your TA achieve when souring. How would you recommend going about that? I've had this question come up a handful of times, which is why I wanted to bring it up. It's really simple. You can just add things that are going to give you temporary hardness into your beer at the end of fermentation. Sorry, at the end of your brew day. Add things like calcium carbonate, and that'll give you more buffering capacity. That's going to require the bugs to kind of produce more lactic acid. Which is then going to give you a higher TA. That's the easy way to do it. It doesn't have to be complicated. You give it more buffering capacity, it's going to eat through it. Yeah, I'm 2 or 3 years ago, you'd asked me what type of beer do I want when it comes to sour. I'd probably say the most sour thing you possibly can, because that's where the industry was. And now I'm like, no, I want a restrained, nicely balanced sour. So I'm hesitant to say you should do that, but because I want it a bit more delicate and a bit more kind of, finessed. But that is a way to do it.
Yeah, I want flavor, not boring kettle sours. I want distinct flavor, and like I guess that's kind of the MO that we're pushing, is that is possible by selecting different strains.
Yeah, I'm sick of drinking kettle sours that taste like bile.
Really, really, the same, right? The reality is that most of the strains out there are the same, and that needs to change.
Yeah. Awesome.
All right. Yeah, that's it for our questions. I think you covered everything that I would have otherwise asked you about. So I want to thank the audience for asking all the right questions. Really appreciate that. Thanks for tuning in. See some familiar names as well. So that's really great to see. And like we said, we're going to be back in July talking about yeast management. And in the interim, we're going to try to do things to keep you guys engaged and interested. You might see me in the lab talking about hazy IPAs or Kvike lagers or something else. But in the meantime, we're gonna try to keep things interesting, and at the very least, we're gonna get these slide decks up on those YouTube videos to download.
Yeah. Thanks everyone for joining us for season 1. We'll see you in season 2.
Cheers.
Awesome. Cheers.